Hey everyone, so last time we saw that we tried to use Gauss's law to help us find magnetic field strengths around wires, but Gauss's law showed us that there is no such thing as a magnetic monopole, that all magnetic fields are dipoles. We're going to have to turn to Ampere. Ampere looked at currents going through wires and came up with a law that you could create what he called Amperian loops. So you can make a loop around a wire like we've seen the magnetic field do, and the magnetic field is tangent to that loop, and if you sum up all the magnetic fields, it would be equal to mu zero times IC. IC being the current that penetrates through that area. So if you think of that loop as a flat disk, if current passes through that surface, then you can calculate the magnetic field strength around that Amperian loop. One thing, the current must be steady, and it's going to work in highly symmetric situations. So things that are not symmetric aren't going to give you good magnetic field strengths. And the B must be parallel to DL. And what do I mean by that? I mean, if you pick this little tiny segment of DL of the wire up here, the magnetic field, if you put your thumb in the direction of current and curl your fingers, you know the magnetic field also points in that same direction. So the magnetic field and the length vector should be parallel. So the way we write Ampere's law is B dot dl equals mu zero IC. IC being the current that penetrates through that area. You can see that B and dl are in the same direction up at the top there. So let's do this for straight current carrying wire. If I want to solve for the magnetic field around this wire, I can write B dot dl, and I know B dot dl is valid because of this current. This current is passing through that flat circular area, so I know I can solve for the magnetic field. Well, the magnetic field at this distance r is going to be constant, so that means I can pull out the magnetic field and I just have to integrate dl mu zero I. Well, dl would be from no length to the entire length around the Amperian loop. The entire Amperian loop here would just be L, and since the length around a loop is the circumference, you'd have B times 2 pi r being the circumference equals mu zero I. Solving for the magnetic field, you get this, mu zero I over 2 pi r, which is exactly what we got with the Biot-Savart law, except now we can just use our Amperian loops. Now, similar to what we did with Gauss's law and Gaussian surfaces and spheres and shapes, if I had a current pass through in the opposite direction, also through my Amperian loop there, well, I have a forward current and a backwards current. This IC is the net current that passes through the Amperian loop. So if there is forward and a backwards current, those currents are going to sum to zero net current, which means that there would be no magnetic field around this Amperian loop. So having currents in opposite directions creates no magnetic field outside of the Amperian loop. So what we can do, similar to what we did with electric fields, is we can use Ampere's law to find magnetic fields inside and outside of current carrying wires. If I want to solve for the magnetic field, let's go outside. I'm going to make an Amperian loop that is outside the wire at a distance little r from the wire. I can see that I do have current passing through my area, and since it passes through the area here, I can use Ampere's law. So the magnetic field will be constant at a distance from the wire, so I have to just integrate dl over mu equals mu zero I. dl again is the length of my Amperian loop, which in this case is a circle again, so the magnetic field outside ends up being mu zero I over 2 pi r. So there, it's the same thing we just saw before. That's the magnetic field outside of a current carrying wire. What if we go inside? You can see this inner surface here is not enclosing the entire wire, so that means I'm not enclosing the entire current. So in this case, if I want to go inside, I have to do the Amperian loop with the enclosed current. Now the enclosed current isn't all of the current, so I have to look at a ratio there, and that's where we're going to look at the current density. Remember, the current per unit area. But this time we're not looking at surface areas or three-dimensional shapes, we're looking at flat Amperian loops. What I could say, if my current density is constant, that the enclosed current that I'm looking for would only pass through pi little r squared, whereas the total current is going to pass through the entire area of my wire. So if I want to solve it again for the current that's passing through the Amperian loop, I can look at this ratio and get rid of the pi's, and what I'll be left with is the enclosed current is a ratio of the total current to the inner radius squared over the total radius squared. So I'm going to put that in for I enclosed. So there is our equation for the magnetic field inside, but now we have to integrate. Anywhere around the Amperian loop, since it's symmetric, we'll have a constant magnetic field. So I really just have to integrate dl here. So dl is going to give me length. The length around the Amperian loop is going to be 2 pi little r for the small Amperian loop inside, and that's going to equal our mu 0 I little r squared over big R squared. Things that can cancel for us nicely is the little radius here and one of the little radiuses on this side. So rearranging this for the inside, you get this for the magnetic field inside a current carrying wire. So you get mu 0 I little r over 2 pi big R squared. So really the only thing that's changing here with the magnetic field is the distance. So as the distance increases, so does the magnetic field strength. And this is what you would see. You'd have no magnetic field strength at the center of that current carrying wire because you haven't really enclosed any current whatsoever. But as you start enclosing more and more current, the magnetic field strength is going to get stronger and stronger until you reach the surface of the wire. Once you get outside the wire, we see a 1 over R relationship as the magnetic field decreases when you get further away. It's not inverse square, but it is 1 over R. It is an inverse relationship. So let's use Ampere's law here with the solenoid. We showed you that there was a very, very long calculus way to solve for the magnetic field strength due to a solenoid, but let's use Ampere's law now. And an Amperian loop doesn't always have to be circular. In this case, you can see the Amperian loop is a square. It's got 4 sides to it: A to B, B to C, C to D, and D to A. So if I want to use Ampere's law to find the magnetic field inside the solenoid, the field must be parallel to the line segments. So let's do Ampere's law for each of those line segments. And the magnetic field says it's straight down here. To test that, thumb in the direction of current, curl your fingers, and you can see that this has current down in the middle here and out on the sides, down in the middle, and out on the sides, just like we saw in the demo today for the homemade solenoid. So if I want to sum up all the Amperian loops, I can do B dot dl along each segment there. Now, if we look at that first segment, A to B is right here. Well, we can see there's a magnetic field, but dl is to the right, and the magnetic field is down. It's a dot product, so both dl and B have to be in the same direction. So right off the bat, there is no magnetic field here. B to C is this segment right here. There is no magnetic field outside the solenoid. Remember, the cancellation happens from these 2 wires on the outsides and summed together on the insides of a solenoid. So since there's no magnetic field out here, there's really no point even to do this integration. So there's no magnetic field outside the solenoid. Let's do D to C. D to C, we have the same issue again. dl is to the left, and the magnetic field is down. They're 90 degrees apart. Dot products need to be parallel, so no magnetic field there. What about that last segment, from D to A? Now we're getting somewhere. We've got magnetic field down, and we have dl in the downwards direction. So B dot dl is going to give me a way to solve for magnetic field strength here because they're both parallel. So I know that this segment is valid here, and since the magnetic field strength is uniform inside a solenoid, dl is just going to be the length from A to D. So why don't we just call that L? So B times L equals mu 0 I. But if you look at this Amperian loop here, there's not just one current that I have penetrating the loop. I've got multiple currents. I could have 3, 4, or however many turns those solenoids have. So I'm going to add in a large N value for the number of turns. And if I want to solve for magnetic field, I'm just going to divide by the length. And if I divide the length over here, turns per length, remember, gives us little n. In the end, the magnetic field for a solenoid, and yes, the magnetic field strength inside a solenoid here is mu 0 little n I, or bunny. But there's an even crazier structure than a solenoid. What if I took a solenoid and bent it all the way into a circle? what we've created here is a toroid. So a toroid is going to create magnetic fields down the center, just like a solenoid, but now I've bent the solenoid into a circle. So let's use Ampere's law to show what the magnetic field strength is along the toroid. So scenario 1, what if R is less than A? So what if I make an Amperian loop that is inside radius A? Well, based off of Ampere's law, B dot dl mu 0 I, right there, to see if there's a magnetic field strength, remember I've got to have a current that passes through the Amperian loop. Here, there is no current that's passing through the loop. So that means there is no magnetic field inside the center. Let's go to the other extreme. If our R is greater than B. Well, if R is greater than B, well, it looks like I'm going to now have currents pass through my Amperian loop. My Amperian loop is all the way out here. And let's see if I have current. Following that wire, as the current comes in, it's going to go into the page here and come out of the page over here. And then go back into the page and then out of the page, and you can see that's going to repeat all the way around. If you look at all those X's and all those circles, all the current that's coming out of the page has a current that actually goes back into the page. So the total net current still adds up to 0, which means outside the toroid there is no magnetic field anyway. So where's the magnetic field? The magnetic field has to be around this orange Amperian loop that they've already drawn for us. So around the orange Amperian loop, do I have currents in there? Yes, I do. I have into the page currents all the way around the toroid. All the out of the page currents are not in my Amperian loop. So that means I can use Ampere's law. So mu 0 I, in this case, how many currents do I have? I have n amount of currents that are passing through, and dl is the length around the Amperian loop. In this case, the Amperian loop is a circle, so it's 2 pi, we'll call it little r, equals mu 0 I n. So to solve for the magnetic field for a toroid, you get this, mu 0 large N I over 2 pi times the radius. So it creates very, very large magnetic fields, and if I have current into the page, that means the magnetic field is pointing in very large uniform loops around the inside and the center of our toroid. So here is a picture of a toroid, and here's a person inside of a toroid, cleaning it, inspecting it, whatever they need to do. They use these for trying to contain fusion reactions. You create very, very large magnetic fields inside the toroid to try and trap plasmas so that you can get those particles to hopefully fuse together and give off energy. So I hope Ampere's law is going to help you out and makes finding magnetic fields just a little bit easier.